So let us get started with what is called as differential analysis of fluid flow. So in the differential analysis of fluid flow, the finite control volume approach is very practical. So in this, what happens is that, so you have the finite control volume approach is very practical and useful, since it, so you have in the finite control volume approach is very practical. So what happens is, in this we use, if we just go here, this is the control volume which I am going to choose. In this control volume, so what happens is that the flow goes inside the control volume, gets out. But what exactly happens inside the control volume, we are not bothered about. So that is why interior of the control volume will act as a black box. But now if you take the differential approach instead of control volume approach, if you take the differential approach or the differential analysis, if you do, what exactly happens near the blade, what are the velocity gradients, what are the temperature gradients, what would be the vortices, whether vortices are there or not, in addition to the forces and the heat transfer rate, here we will get to know what are the temperature gradients, velocity gradients, pressure gradients. So we will get, that will be useful in explaining the heat transfer rates, heat fluxes, the forces acting. So here in the coming lectures, we are going to adapt what is called as differential approach or differential analysis. So the heading we are going to write as differential analysis. Differential analysis. So the point what we are going to do is, what happens when a fluid particle moves from one location to another location within a time span of delta t. That is what is our focus. So what all things it can happen? So what all things can happen is that it can undergo, the general motion can undergo translation. That means there will be no just it translates, there will be no change in the shape. Linear deformation, here also there is no change in the shape. The surfaces which are perpendicular will remain perpendicular, but there can be stretching or compression. And in case of rotation, here again the surfaces can remain perpendicular, but they may undergo angular motion, that is rotation. In addition, it can also undergo angular deformation. So when a fluid particle moves, it can either translate, linearly deform, rotate, or angularly deform, or all of this can occur when a fluid particle moves from one location to another location within a time span of delta t. So now in the next few minutes, what we are going to do is that we shall try to mathematically represent this translation, linear deformation, rotation, and angular deformation. So how do I do that? So now let us start with translation. What happens in translation? So I have a fluid particle O, A, B, C. O, A, B, C. Now it is having velocity u here and the velocity v here. Now after time delta t, it translates and reaches a new location without undergoing any deformation. So this distance what it has travelled is u delta t. Similarly, the distance which it has travelled here is v delta t. Okay? But the main thing is there are no velocity gradients during translation, there are no velocity gradients, number 1. Next is that that means that it is my fluid particle is able to translate itself from one location to another location. Now let us take up what will happen if there is linear deformation. Linear deformation. Linear deformation. So, I take a fluid particle O, A, B, C. Again, the velocity here is u and the velocity here is again u. Now, what is the velocity at A? What is the velocity at C? So, the velocity at A is, there is a variation over the distance delta x, okay, that is u plus del u by del x into delta x. That much variation has occurred in the velocity gradient because of the velocity gradient del u by del x. So, here u plus del u by del x into delta x. So, this is the velocity at A and this is the velocity at C. Now, what is the consequence of this on my fluid particle OABC? OABC, what is the consequence of this? So, if the consequence of this is that it will cause stretching. So, the fluid particle has gotten stretched. So, what is that distance by which it has gotten stretched over a time delta t? So, that is this difference between u plus del u by del x delta x minus u. So, that is you get del u by del x into delta x into delta t. So, that is what is this stretching has occurred. So, but this stretching has occurred, remember, because of gradient of u in x. That is very, very important. So, this is the stretching. So, what is the change? Stretching of volume. So, what is the stretching of the volume element in volume? What is that? It is del u by del x into delta x into delta t for the complete element, which is a parallelepiped, that is delta y delta z. That is, I consider the fluid particle like this, okay, if that is the case. Now, so what will be the rate at which the volume delta v is changing per unit volume due to the gradient, or it is not required, it is understood, it is because of the gradient. So, that is 1 by delta v d of delta v divided by dt is equal to limit as delta t tends to 0 dou u by dou x into delta x divided by delta t. This delta v, remember delta v equal to delta x, delta y, delta z. So, you get this as dou u by dou x. So, similarly, you can, if you take the stretching in the y direction, so you get del v by del y in the y direction, stretching in the z direction will be del w by del z in the z direction. So, net change 1 by, if you take the stretching in x, y, z directions parallelly, d of delta v by dt is equal to del u by del x plus del v by del y plus del w by del z is equal to, this is what is called as volumetric dilation rate. Volumetric dilation. It is getting dilated, that means it is getting swollen. That is what is dilation rate means. This, but for incompressible fluids, what is the characteristic of the incompressible fluid? For the incompressible fluid, density is constant. If the density is constant, we know that mass equal to density into volume. So elemental mass has to be conserved. Elemental mass is conserved by conservation of mass. In that is the case for incompressible fluids, if density is constant, change in volume will be 0. That means for incompressible fluids, del u by del x plus del v by del y plus del w by del z, the dilation rate will be 0. That means it can undergo deformation, del u by del x, del u by, there can be stretching in the x, stretching in the y, stretching in the z, but the net change in the volume has to be 0. So that is what is the consequence of the linear deformation. So now what we will do is, we shall take up what is called as angular motion and deformation. So you have a square, that is a fluid particle, O, A, B, C. Now you have the velocity here, U, V, okay. Now the velocity change of V in the x direction, in over length delta x, here it will be V plus. Now V has changed over length delta x. So that means the gradient of V in the x direction. So dou V by dou x into delta x, that is what you get. Now let us take up what will be the variation in U over the length delta y. That will be U plus variation of U in y, del U by del y into delta y. So now what is the consequence of this? Like earlier, here the consequence is that it is going to undergo the angular deformation or rotation. So the particle OA has rotated by an angle delta alpha and reached position A prime. And what is this? What is this distance? This distance, this has occurred over a time t. So that is the difference between V plus del V by del x minus V. So that means you get this as del V by del x into delta x into delta t. Okay. So now similar to this, what happens to OB? It will undergo rotation. OA will undergo rotation to B prime or angular deformation, that is delta beta. So what is this distance BB prime? That distance is the difference between U and U plus del U by del Y into delta Y, that will be over a time delta t. So that is del U by del Y into delta Y into delta t. So that is what happens here. Now let us try to find tan delta alpha. What is tan delta alpha? Tan delta alpha can be approximated for smaller angles as delta alpha, which is tan delta alpha is opposite by adjacent, that is AA prime divided by OA, AA prime divided by OA, that is dou V by dou x into delta x into delta t divided by OA, which is nothing but delta x. So you get this as dou V by dou x into delta t. Now if you take for the angular motion, that is omega OA, what is omega OA? It is angular velocity of OA, that is omega OA is limit as delta t tends to 0 delta alpha by delta t, that is limit as delta t tends to 0 delta dou v by dou x into delta t divided by delta t, which is nothing but dou v by dou x. So, dou v by dou x means the angular velocity of OA. Now, similarly, tan delta beta for smaller angles I can write this as delta beta, which is equal to BB prime divided by OB, which is equal to del u by del y into delta y into delta t divided by delta y, that is equal to dou u by dou y into delta t. So, omega OB is the angular velocity of OB. So, omega OB equal to limit as delta t tends to 0 delta beta by delta t is equal to limit as delta t tends to 0 dou u by dou y delta t divided by delta t is equal to dou u by dou y. Okay. So, this is omega OB. Now, the rotation, this is the OA and this is OB. This net rotation will cause the rotation in the z direction, that is perpendicular to this z direction. So, we can call this the net rotation omega OA, that is OA to OA prime, this is in counterclockwise direction, counterclockwise. This can be considered as positive, and OB to OB prime, it is in clockwise direction, so that I can consider as negative. So, omega z can be considered as the average of, because it is a very small rotation, small angle has changed, that is why I can take the average, because it is varying linearly, I can assume that. So, omega z is equal to half of omega OA plus omega OB. That means I get this as half of dou v by dou x minus of dou u by dou y. So, this is omega z. Now, let us write omega z equal to half of del v by del x minus del u by del y. Okay. Now, this is half of that. Now, omega x equal to omega y equal to omega x, that is rotation of the element about the x axis, this is about z axis, rotation about z axis. This is half of, you can derive the same way, del w by del y minus of del v by del z, this is about x axis. Similarly, omega y equal to half of del u by del z minus del w by del x, this is about y axis. So, omega equal to I omega x plus j omega y plus k omega z. As you know, I, j, k are unit vectors in the x, y, z directions. So, we can define, or omega is defined as half curl v, that is the velocity vector v. So, that is half of del cross v. What is del cross v? Del cross v is nothing but I, j, k. This is del by del x, del is del by del y, del by del z, and this is u v w. That is v is I u plus j v plus k w. Okay. So, similarly del I think I have written that, that's fine. So if you expand this, I into del W by del Y, that is this, minus of del V by del Z, that is this. Okay. So now J plus J into, this is opposite, that is del U by del Z minus of del W by del X. Okay. So that is what we do. So now plus K into, you get for K into, you write these two, that is del V by del X minus of del U by del Y. So you can check that these are same, this is nothing but omega X, this is nothing but omega Y, this is nothing but omega Z. So we define what is called as vorticity, that is omega, capital Omega equal to twice the angular motion, that is equal to del cross V. For irrotational fluids, del cross V is 0. Okay. So now the angular deformation, so what happens to the angular motion? So if you go back, so you had this delta alpha and delta beta. Delta alpha and delta beta is the angular deformation which has occurred. So the shear strain delta gamma is equal to delta alpha plus delta beta. So let us write this. So shear strain, so shearing strain is equal to shearing strain delta gamma is equal to delta alpha plus delta beta. So rate of shear strain, if I want rate of shearing strain is nothing but gamma dot is equal to limit as delta t tends to 0 delta gamma by delta t, that is limit of delta t tending to 0, delta alpha is nothing but dou v by dou x into delta t, delta beta is nothing but dou u by dou y into delta t, that is there here. So I have just written from here only. Okay. So if I write that divided by delta t, so you get gamma dot as dou v by dou x plus dou u by dou y. This is the shearing strain rate. Okay. Now if it were to be, this is the shearing strain rate if it is undergoing deformation like this. But of course, if the fluid particle, this OA has rotated in the counterclockwise and OB also has rotated in the counterclockwise direction, and if dou u by dou y is equal to minus del v by del x, then it undergoes rotation but not angular deformation. There is no angular deformation in that case, that is 0. So element is simply rotated as an undeformed block, but that is possible only when del u by del y equal to minus del v by del x. Okay. So the point to be taken away is that if the variations in the velocity in the directions, this is causing linear deformation, that is del u by del x, del v by del y, del w by del z. If these variations are occurring, that is u in x, v in y, w in z, if this is happening, that is what is called as linear deformation. But if there are cross derivatives, that is del u by del x velocity, u in x, v in y, w in z, these cause linear deformation. That means del u by del x causes stretching in x direction, and del v by del y stretching in y direction, del w by del z is stretching in z direction. So, but cross derivatives, what about cross derivatives? If you have cross derivatives, if you have cross derivatives, So what is that we will have is del u by del y, del v by del x. These can cause either angular deformation or rotation. So please remember here afterwards, physically you should not say that u is varying in x when you say del u by del x. It means that it is stretching. When you say del u by del y, you should physically imagine that it is either undergoing, the fluid particle is undergoing angular deformation or it is undergoing rotation, depending on the consequence how the del u by del y compares with itself with del v by del x. So that's what we need to imagine. So now what happens is that in case of incompressible flow fluid, incompressible fluids or flow field, incompressible flow field, the fluid element undergoes translation. It can undergo translation, distortion or rotation, but it does not grow or shrink. It does not grow or shrink. Why? Because change in volume, we saw that change in volume is 0. What is the change in volume? Del u by del x plus del v by del y plus del w by del z was 0. There can be stretchings, but it can lead to compression corresponding, and net change in volume is 0 in case of incompressible flow field. But in case of compressible flow field, my fluid element can, in addition to undergoing translation, distortion and rotation, it can also grow or shrink. That means there is possibility for change in volume in case of compressible fluids. So that's what is shown in this figure. You can see that in incompressible flow field you can either have the change in the volume, that is there is no change in the volume in case of incompressible fluids, and in compressible fluids there is shrinkage or growth. So that's about the stretching and what happens to a fluid particle. In the next class we shall take up conservation of mass, momentum and energy. That is what is going to lead us for the differential approach. Thank you.